why do we talk about stereochemistry in the first place? Let's look at a real-world example. This is a molecule known as thalidomide, and it was commonly used back in the 70s as a sleep aid in pregnant women. This molecule on the left, this stereoisomer, is well known to induce sleep, and it's very effective. However, on the right, this stereoisomer causes severe birth defects. Pretty severe complication if you don't know what you're looking for, which is these chiral centers right here. Let's look at another example. So let's start with a molecule, pretty simple one. Let's start with 2-pentanol right here. And then we'll draw the mirror image on the other side. We see we have the hydroxyl group on the right because we're looking in a mirror. But let's go ahead and flip it over. Put it on the left. Make sure we know that this is in fact a different configuration. Okay, so we have one stereoisomer, 2 in fact. Do we have more than that for 2-pentanol? Well, how do we know? Let's draw it again, hydroxyl group. First question to ask, how many stereogenic centers are we dealing with? So we know there's one right here. It seems pretty obvious that the others aren't. But let's take a look at these carbons. Right here, we have the carbon with the methyl group, hydroxyl group, hydrogen group, and our propyl group right here. What about these carbons here? Let's take a look. Okay, how about this one? We have carbon, and immediately we see 2 hydrogens. Immediately we can see that there's a plane of symmetry that lends itself right there. So none of these are going to be chiral centers. So we have one. Second question. We can determine how many stereoisomers there are for a particular molecule with the equation 2 to the n. That being 2 to the n. N being the number of stereogenic centers. So we have up to 2 to the n stereoisomers. That'll be important. Okay, so 2 to the 1 equals 2. We have 2 stereoisomers, 2-pentanol. Okay, draw the mirror image here. We can see it. And there we go. We have our 2 stereoisomers. And we can have up to 2 to the n. Why did I say up to 2 to the n? Let's take a look at another example. Let's look at 2,3-dihydroxybutane. Okay, here we go. I'm not going to draw on the hydrogens because we know where they go. They're projecting backwards. Okay, how many stereogenic centers are we dealing with here? Well, off the bat, you should be able to see that there are 2. And I'll draw one of these out, but just be aware that the other one is essentially the same, just, you know, in a different spot. Okay, methyl group, hydroxyl group, and here we have our R group on the side. Okay, so those are basically the same. So how many stereoisomers do we have? 2 to the n. That's 2 to the 2 equals 4. Right? Yeah? Okay. Well, let's draw them out. Let's see what we can do. Let's just move these hydroxyls around. In every way we can imagine that these would be different stereoisomers just by moving these functional groups around. Okay. We have one away, one towards, both away. 1, 2, 3, and 4, starting with our original one. Let's take a closer look at 2 and 4. Okay, when we draw these out, hydroxyl group here and one away, and the mirror right here. But right here we have a sigma bond, which remember, we can rotate freely around our sigma bonds. And when we do that with 2,3-dihydroxybutane, we end up with both of our hydroxyl groups projecting towards us, and we can rotate this sigma bond, end up with the same thing. You can see how you could easily rotate that around and end up with exactly the same molecule. So we have 2 identical stereoisomers. So what is that? Well, we can also see we have a plane of symmetry running through these after we rotate it around the bond right there, which we know means that these are in fact achiral. Okay, so we have what's called a mesocompound. A mesocompound is actually an achiral pair of diastereomers. Let's look at a more typical example of up to 2 to the n. This one should get us all the way to 2 to the n. So let's take a look right here, 2,3-dihydroxypentane. Okay, we have our 2 centers. 2 to the n equals 4 potential stereoisomers. Let's draw these out. Let's move these hydroxyls around. Right here, this is the one we started with. And here we have another one. Let's just move that bottom one back. Okay, move the front one back, leave the bottom one forward. And let's move them both back. So we have these 4 potential stereoisomers. 1, 2, 3, and 4. Well, how do these relate to each other? We can draw these out, but what do these mean? Well, let's take a look at these and how they relate to each other. Let's look at 1 and 4. They look like they're pretty much opposites, right? We can look at these chiral centers and they're projected opposite directions. So 1 and 4 are in fact enantiomers. Okay, and actually we can see the same relationship between 3 and 2. Also enantiomers. But what exactly is an enantiomer? Well, enantiomers are non-superimposable mirror images of each other. Okay, we can draw these here just to prove that these are non-superimposable mirror images. Okay, and there's our mirror image of number 1. Let's flip it, and it looks pretty familiar, doesn't it? Right there. But it's not superimposable. We have one pair of hydroxyls projected back and one projected forward. So some properties of enantiomers, they have the same chemical properties as you could imagine. So I mean boiling point, melting point, point of sublimation, all of those are going to be the same, but they're going to be different in a couple of aspects. One is they rotate polarized light in different directions. We're not going to get into that. The other, like we saw with thalidomide, is how they react with other compounds. That's the most important differentiation. Okay, well what about these other ones? What about 1 and 3? What about 1 and 2? What about 4 and 3 and 4 and 2? Well, these all sort of have the same relationship. They're not mirror images, which we can tell by drawing them out. I'm not going to do that. And they're also not superimposable. When you have non-mirror images, not superimposable, but still stereoisomers, you have something called a diastereomer. So diastereomers, my definition, very simple. Diastereomer is a stereoisomer that is not an enantiomer. Okay, well, let's take a look at enantiomers again. This is everybody's favorite analogy. Enantiomers are a lot like hands. Okay, so we have our left hand. Okay, and our right hand. And our hands, if we're holding them like this, look a lot like mirror images of each other. So these are our palms. We're looking at our palms. They look like mirror images, okay? But they're not superimposable. And to all the smarty pants in the class, let's flip this over, put the thumb on the same side. Now, surely it's superimposable. But no, this is the back of our hand, just like with a molecule. Not even this is superimposable. So enantiomers, a lot like hands. That's a good way to remember them. So let's talk about the elephant in the room. We've been ignoring alkenes this whole time. So can alkenes be stereoisomers? Well, let's take a look at an example here. Okay, let's draw this nice disubstituted alkene right here. Okay, so let's look at these carbons. Are any of these carbons chiral? Are these chiral centers? Well, we have to consider an alkene a double bond as if it's 2 bonds to the same group. So we have our 2 bonds to carbon in an R group here. And those are the same. We can see a plane of symmetry immediately. So no, alkenes are in fact inherently achiral. But can they be stereoisomers? Well, let's draw this back here. Let's draw these 2 methyl groups, this disubstituted alkene. And let's draw it like this now. Let's put these methyl groups on the same side. Well, these are actually 2 different configurations. We have a trans and a cis isomer. So this is just another form of stereoisomers. These are called cis-trans isomers. And these are actually a form of diastereomer. So for stereoisomers as a whole, remember we have our enantiomers and our diastereomers. And on the other hand, sort of treated differently, we have cis-trans isomerism. And yeah, they can in fact be stereoisomers.